Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series delivered for the BSc Physical Sciences students who are doing the paper on applied electronics, in continuation with what we have been seeing in the unit 4 of the paper. We have been seeing natural radioactivity, and in this lecture the contents will be gamma radiation, conditions for equilibrium, nuclear equations, decay of radionuclides. I told you in the last lecture that the artificial radioactivity consists of 3 kinds of emissions. One is alpha particle, the other is the beta particle, and the third one is the gamma radiation, and the distinction between these 3 were evaluated by Henry Becquerel himself. Along with Becquerel, so many other people whose names were mentioned in the last lecture, they were also responsible in determining the nature of alpha, beta, gamma radiations. As I told you in the last lecture, alpha particle is nothing but the helium nucleus. You look at a periodic table, helium contains 2 electrons, and in the nucleus there are 2 protons and 2 neutrons. So, the mass number is 4, that is the alpha particle. That one comes as follows, as shown in the diagram. From uranium 238, you have the alpha particle coming out, right? The alpha particle is coming here, and 238 becomes 234, that is 4 mass number is reduced by 4, because the 4 refers to the mass carried by the alpha particle. So, alpha particle is nothing but the helium nucleus containing 2 protons and 2 neutrons. The mass number is 4, okay? That is the alpha particle. Now, what about the beta particle? Now, before going to the beta particle, let me introduce to you what is the parent nucleus and what is the daughter nucleus. Parent daughter nuclei. Alpha particle of uranium 238, you got 238, that is called a parent nucleus. The decay event occurs, and the decay leads to emission of an alpha particle with mass number 4, and the daughter number, as I told you, this is called the daughter nucleus, right? 4, you got a 4, that is the mass number. You got the daughter nucleus, which obviously should be having the mass number 234. Out of 238, 4 has gone, 4 has been given to the helium. So, 234 plus 4 makes 238. So, the mass number is reduced in the daughter nucleus by 4. So, you got thorium, uranium being converted into thorium with the mass number 234. This of course we call as nuclear transportation. The nucleus has been changed from uranium to thorium with the emission of an alpha particle, right. So, this is called the parent nucleus, this is called the daughter nucleus, and that is the emission of alpha particle. And the same thing you see the americium nucleus with a mass number 241, it emits an alpha particle and the resultant nucleus is neptunium. So, americium with mass number 241 is transformed or it undergoes transportation to neptunium nucleus with mass number 237. 237 you got 4 here, 237 plus 4 makes 241. So, this is a parent nucleus giving rise to daughter nucleus after the emission of the alpha particle. Therefore, alpha particles can be emitted from uranium or americium. And now we will move on to the beta particle. From the applied electric field or magnetic field, people were able to find that the beta particle is nothing but the electron. Alpha particle is not a proton, it consists of 2 protons and 2 neutrons, that is nothing but a helium nucleus, whereas beta particle is an electron. Of course, the mass is very small and they travel farther than the alpha particles and have the ability of penetrating the skin. I will come to that later, the penetrating power of alpha, beta, gamma, a comparative study. A beta particle or an electron which is denoted by this symbol -1, that refers to the charge of the electron. The mass is taken as 0, that is beta, or the instead of beta you can have electron, is emitted from thorium. So, you can have from thorium also, you can have a daughter nucleus protoactinium from thorium, right. Thorium gives rise to an electron and the remaining things goes as protoactinium. The point to be understood is you got the atomic number is 90 and protoactinium will have the atomic number 91 because you got -1 here, the charge associated with the electron. 91 minus 1 will be 90 because the charge should be conserved. In all the nuclear reactions, the charge, mass and many other physical quantities ought to be conserved. So, the conservation laws are applicable, should be applied. So, thorium with mass number 234 getting converted into protoactinium with the same mass number, but the atomic number changes from 90 to 91 and a beta particle is emitted. So, this is an example of beta emission, and gamma rays are nothing but high energy photons. For that, how do you get high energy photons? You have to look at the nuclear energy levels. How do you get this light here? Light from the mercury vapor lamp or the Lyman Balmer series in the hydrogen spectrum. It is because of the electronic energy levels. Similarly, you should look at the nuclear energy levels, the energy levels of the different nuclei. When the electron is coming from the higher state to the lower state, the nuclear energy difference will be coming out in the form of photon. The electromagnetic spectrum shows different forms of radiation, and the gamma ray having the highest energy, making them potentially most dangerous to humans and so on. And the gamma radiation, the example will be the parent nucleus cobalt giving rise to the daughter nucleus nickel 60. You got cobalt 60, nickel 60, and you got gamma rays coming here, right. The parent nucleus gives rise to an electron, right. An electron here the daughter nucleus will be again the mass number remains the same 60, and electron is coming here, and along with that there will be gamma radiation. In the next slide I will be showing the energy levels, right. So, the energy levels of the cobalt to nickel, okay, the energy levels are responsible for the emitted energies associated with the gamma radiation. They are the energies associated with the gamma radiation. So, when the nucleus goes from this energy state to this energy state, the energy difference 1.1732 million electron, MeV refers to million electron volt, that gives rise to the gamma radiation. So, this energy should be equated to h nu, as all of you know. Therefore, the example will be, you have cobalt 60 giving rise to nickel 60 and an electron and 2 gamma photons. So, the gamma ray, you got that here, it consists of 2 photons. So, the process is the following: cobalt nucleus is getting transformed into nickel nucleus with the emission of an electron and 2 photons. That is example for gamma emission, okay. And the point to be understood or remembered is 60 and 60. So, the mass number is conserved. Now, what about a charge? You have got 27 here, charge also is to be conserved. I have written charge conservation. 27, you have got 28 here, minus 1 here. Because it is 28 and you have got minus 1 here, the charge is conserved. The mass number should be conserved, the charge should be conserved, all the conservation laws should be obeyed in nuclear reactions, okay. These are the energy levels of the nuclei of cobalt and the nickel, right. From the energy levels one can explain how gamma radiations are coming and what are the energies associated with the gamma radiation. Gamma radiation is nothing but light radiation. It is something similar to light radiation, but the energy is so high that it will be able to penetrate even lead sheets, paper, mica, all the materials will be, even cement block will be penetrated by the high energy radiation, okay, that is the gamma radiation. So, gamma radiation is nothing but photons. Here is the comparative study between the 3 radiations coming from any natural radioactivity. Natural radioactivity consists of alpha, beta, gamma. Alpha, as you know, it is nothing but the nucleus of the helium atom. Second is beta is an electron, gamma is something like light radiation, but much more powerful, the energy is very powerful. So, the power associated with gamma radiation is clearly depicted in this diagram. You see, alpha radiation is coming here by the human skin, it can be stopped. The penetrating power is not very high. The human hand will be able to stop the alpha radiation, or paper stops alpha, whereas the beta radiation will penetrate the paper or thin mica will be penetrated, the skin will be penetrated, the beta particle electron will pass through the skin and it will be stopped by a thin aluminum, will be able to stop the beta radiation, the electrons can be stopped. On the other hand, gamma cannot be stopped even by aluminum block, and even a thick lead block will not be able to stop the gamma radiation. If you allow the gamma radiation, it will pierce through the wall. You have got the walls here, and the gamma radiation will be able to pierce through the walls. So, the gamma radiation is having very high energy. The gamma radiation used to as a NDT tool, non-destructive tool, to detect the flaws in the components and so on. So, gamma radiation is a high power radiation. It is much higher than, look at the electromagnetic spectrum, it is much higher than X-rays. The thick lead reduces gamma, it does not stop, and it has got biological and medical implications, right. You use gamma ray for very many applications. The radioisotopes for curing cancer and many other biological and medical applications are associated with the gamma, and so you talk of gamma camera and so on. Okay. We now talk about what is called the positron emission. When you are talking about these nuclear transportations, what do you mean by nuclear transportation? I told nickel, cobalt going to nickel and americium. I mentioned about various different nuclei, americium, protoactinium and so on. So, the nuclei are transformed, they are called the nuclear transportations. So, similarly now if you have carbon 14 giving rise to a beta minus, that is electron, then you have go to nitrogen 14 containing 7 protons and 7 neutrons plus what you call a anti-neutrino and electron. So, the electron will be coming from carbon 14 giving it electron. On the other hand, carbon 10 will give rise to a positron. What is a positron? Positron is a antiparticle of the electron. Electron has got a negative charge and positron is having a positive charge, and the mass is exactly the same as that of the electron. Here again I want to impress upon you the charge is conserved. You have got 6 protons here, and when you have here 5 protons, the boron has got 5 protons, but another positive charge is coming from positron. So, positron carries a positive charge, you see a plus sign here. So, 5 plus 1 6 will be equal to 6 protons. The charge is conserved, 6 positive charges give rise to 5 charges carried by boron, and positron carries a charge plus. So, that makes the charge conservation, the charge is conserved. So, positron emission is due to this reaction. It is called the beta minus is the electron, beta plus is the positron. You see the positron here, you got the electron here. The positron emission, the example will be carbon 10 going to boron 10 plus neutrino and a positron. You got a positron, right. Now, what do you use a positron? Have you ever heard of PET? In the All India Institute of Medical Sciences or in Chennai, in some of the hospitals, you got PET. What is PET? Positron emission tomography. PET is positron emission tomography. We should be able to identify or differentiate between the malignant and non-malignant cells. In the human system, the cancerous cells or differentiating non-cancerous and cancerous cells will be done by PET. A PET is a very good tool. It is a positron emission tomography. You have a CAT scan and similarly PET scan. A positron beam can be used to find out the spread of cancer in the human or the animals. A positron is nothing but an antiparticle of the electron. Here comes another example, potassium with mass number 39 giving rise to argon with again mass number 39 and an electron. Now, with regard to the charge conservation, you got 19 is the atomic number, here you got 18, 18 plus 1 makes 19 and 39 plus 0 is 39. So, the mass number is to be conserved, the charge also is to be conserved, 19 here 18 plus 1 that is 19. A positron is emitted during this reaction. There are very many reactions which are shown in this table, wherein you have got E plus emission. E plus is the positive electron, that is the positron, right. E plus, E minus is the electron, E plus is the positron. So, these mostly proton rich radionuclides are used in positron imaging. Positron imaging is nothing but the PET scan, which is of immense use in oncology, in the field of cancer treatment. You screen the patient, you see the area where you got cancerous cells using what you call a positron emission tomography. Now, the commonly encountered radionuclides, that is the one that we will be discussing now. Which nuclides are radioactive? Whether all nuclei in a periodic table, whether all atoms give rise to radioactivity. As I told you, this question was raised by Madame Curie after the discovery of radioactivity by Becquerel. She thought what other nuclei, other atoms will give rise to radioactivity, and it is found that radioactivity is given out by nuclei whose atomic number is greater than that of bismuth, which is got 83 protons. 83 is the atomic number of bismuth, and the heavier nucleus or the heavier nuclei will be able to give out alpha, beta, gamma. So, the natural radioactivity will be coming from heavier nuclei. The heaviness should be greater than 83, and those nuclei, their atomic number is greater than 83, they are called heavy nuclei. I will come to light nuclei whose atomic number is less than 83 or less than that of the atomic number of bismuth. They are called the lighter nuclei. These are the heavier nuclei. Okay. So, the nuclei with fewer than 83 protons, if the proton number is less than 83, they are called light nuclei. While there are hundreds of radionuclides, many of them are rarely encountered. People are much more likely to encounter a few that are used routinely for medical, military or commercial purposes. So, the radionuclides are got lot of applications. The list below discusses 6 radionuclides. They are the ones most commonly used and most commonly found. Some 3000 nuclides have been discovered thus far, and most of them are unstable. 6 commonly used radionuclides are the following: americium 241, cesium 137. Where do you find cesium in a periodic table? In the first group you got cesium, right? Cesium with atomic number 55. 137 refers to the mass number of protons and the number of neutrons. Cobalt 60. Cobalt is again cobalt therapy. Where do you use cobalt? Cobalt is in all cancer hospitals use cobalt, iodine, cesium, strontium. Again, iodine has 2 mass numbers, 129, you got 131, strontium 90, technetium 99. Technetium is again another radioactive element in a periodic table, one of the elements which has got a HCP structure which is radioactive is technetium. These are some of the commonly encountered radionuclides. Unstable nuclei decay by spontaneous fission, which are unstable. The nuclei which are having their atomic numbers greater than that of bismuth, namely 83, they are unstable. They emit alpha particle, beta particle, gamma emission and electron capture in order to achieve stability. Electron capture is another process during the decay processes. By electron capture, the nucleus becomes more stable. The stability of the nuclei depends upon the neutron to proton ratio. I told you, when you go to heavier and heavier atoms, right, and especially atoms whose atomic numbers greater than 83, with Z is 83, the nucleus becomes unstable. Not only does it become unstable, the important criterion for a nucleus to be unstable depends upon the neutron to proton ratio. N refers to the number of neutrons contained in the nucleus, and Z refers to the number of protons, right. It is the charge of the atom, the number of electrons, and the number of protons. So, the N by Z is the one that is responsible for the stability of the nucleus. And again I will repeat, the nucleus with Z 83 and above are unstable. So, they will be responsible for natural radioactivity. We will be talking about very many radioactive series. The atoms which are radioactive will decay. We will be talking about half-life period and so on, and finally they emit alpha, beta, gamma, etc., all the kinds of radiations until they go from the unstable state to a stable state. Lead is stable. Radioactive decay by particle emission or electron capture changes the atomic number of the radionuclide, whereas the decay by gamma emission does not. In the radioactive decay, particle emission or electron capture may be followed by isomeric transition. In all decay processes, the energy, mass and charge of radionuclides must be conserved. This is the point I have been repeatedly telling. The charge should be conserved, mass and energy in all the nuclear reactions are to be conserved. Examples of each of the decay processes which I mentioned earlier are given here in the slides to come. Alpha decay, as all of you know, uranium 235 will go to thorium 231, and alpha particle whose mass number is 4. Mass number 235, 231 plus 4, 235, the mass is conserved. Here the charge 90 plus 2, 92, the charge is conserved. Now, what is beta decay? A neutron becomes a proton, giving rise to electron. So, that is the beta decay. And similarly, now you have got the positron becoming a neutron and an electron here. Then here comes the electron capture, giving rise to gallium going to zinc. So, these are some of the decay processes which I wanted to tell you. Now, let me pass on to summary of this talk. Almost all elements that are heavier than bismuth, which has got 83 protons, have an unstable nucleus. Some of the commonly encountered radionuclides are americium 241, cesium 137 and cobalt 60. Natural radioactive decay series are uranium 238, uranium 235 and thorium 232. Unstable nuclei decay by spontaneous fission, alpha particle, beta particle or gamma emission or electron capture in order to achieve stability. The questions which I am going to ask now to test your understanding are: what are radionuclides? Mention the various radioactive decay modes. Describe the penetrating power of the different radiations. What is positron emission? With this we come to the end of this lecture. The different decay series which I mentioned will be discussed in the lectures to come. Thank you.